Chapter 3, Section 3, Calculating Changes in Free Energy. Now, when we look at that redox tower, it allows us to couple who's giving up, who's accepting, and we can help it when we're looking at calculating the free energy. Remember that delta G. If you remember from your Gen Chem, delta G equals, was it RT plus, delta H, and then I think it was E, something like that. It's been a while. Well, they've now come up with a different way, since we're now going to be looking at delta G naught prime. Remember, that's going to be in that 1 atmosphere at 25 C, everything at 1 molar, blah, 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 blah. Well, instead of doing the whole, delta H, T, R, T, delta H, blah, 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 they now look at it as delta G naught, the change in the free energy in that reaction, is equal to the negative of the number of electrons transferred times the Faraday constant times the delta E, that redox potential, that reduction potential that we talked about last section. So you go through and you look at, this reaction right here. When we go and we try to determine the breakdown of this compound, plus hydrogen plus 2 would give us carbon dioxide. So this has been consumed and we're releasing water. You can calculate it using, like I said, the reduction potentials, or what they refer to as delta GF, which is another, constant based on G, delta G. What's in the products, what was in the reactants you began with. Again, negative 849 kilojoules per reaction, negative 852 kilojoules per reaction. They're not exactly the same because you're using slightly different yardsticks to measure things, but they're of approximate equal, being approximate equal, which in all intents and purposes, that's what we're looking for more as, because this is going to be used as a relative term to compare to other reactions, not as a set fact, set in stone, that this reaction here has this exactly, and this is what we're going to call it for the time immemorial. So calculating from the free energy of formation. What's the free energy in these substrates? What's the free energy in these products? What they call the reactants, the products. It's a different way of looking at it. It's a different way of measuring things. But again, it gives us a relative numbers that we can go and compare. So you go and you look at the free energy of certain compounds. Remember, this is kilojoules per mole. Using their yardstick and their way of measuring things, say like our friend glucose has negative 917.2 kilojoules per mole of energy in its chemical bonds. All those free, excited electrons, the carbon-carbon bonds, all of it. You go look here, ketoglutarate, our sugars, or our, short chain carbons, succinates, lactates, the amino acids all have quite a bit. What's interesting though, if you go over here and you look at the gases, nitrous, nitric oxide, 104, 86. These are extremely positive. That means there is very little kilojoules per mole of the delta G. This means that these are going to be extremely endergonic in their reactions. So you take A plus B yields C plus D. free energy, C and D, are products, minus the free energy you started with in the reactants or the substrates, A plus B. Positive means that it's going to be an endergonic. Negative means it's going to be an extremely exergonic reaction occurring. Yeah, here's, as I mentioned before, the RT, minus the delta HE, or now they do it, delta G prime plus RT, natural log of the, equilibrium constant. Wow, cannot talk. Where the R and the T are physical constants. The equilibrium constant is going to be based on, whether or not the reaction is more inclined to go to the products or more inclined to be reversible towards the reactants. Yeah, this is, showing you mechanisms for going through and calculating delta G and looking at it at different carbon sources, and 1 molar, 100 millimolar. And yeah, I'll just let you read that on your own.